Greetings, everybody. It's 7:30 a.m. Pacific time on January 28th, 2026. My name is Timur. We have Seth with me online
Hello.
today. Thank you for your interest in Mat3ra.com and welcome to our webinar, Mat3ra 2D series. We created this webinar series to highlight the capabilities of the open source code base for the design of two-dimensional materials. As you can see on the next slide, the capabilities include design of multiple realistic atomic arrangements, like interfaces, surfaces, including defects, grain boundaries, and many other realistic materials arrangements. This is the fifth webinar in our monthly series, and today we're going to highlight reproducing interfaces studied in multiple well-known peer-reviewed publications. Next slide. Now let's briefly go through the rules of engagement. Everybody who's here today should be Mat3ra.com user, but even if you are not, you will be able to benefit from this code base because it's all open source. And if you have questions at any time during this presentation, you're welcome to ask questions either by using the Q&A or by using the chat in the Zoom application. And we're recording this and we'll be distributing later through YouTube. All right, now without further ado, Seth, please go ahead.
Welcome to Mat3ra 2D webinar series. This is episode 5, where we reproduce real-world interfaces from well-known publications. First, we're going to take a look at the presentation to give you an overview of our approach, and then we're going to get to hands-on experience and create the structures. One of the challenges in material science today is that the data used to train machine learning models is example of simple 3D crystals, while for the applications in the real world, you need structures that are more complex, such as surfaces, interfaces, and defects. And we need a way to generate such structures. For that, we created an easy-to-use Python framework called Mat3ra Made for the design of 2D materials. Our approach has well-defined data structures to help organize information in a database and make it easier to build machine learning models in the future. We demonstrate the application of our approach with a set of Jupyter notebooks that can be ran in any web browser. And we primarily focus on 2D materials because we believe this is an area of increased interest, and all of the important electronic and batteries research is focused here. Here we can see examples of the structures that were created using our tools. We have grain boundary with passivation, interface with the intercalation, 2D interfaces of other types. Our implementation includes 5 components. First is the set of data standards stored in Mat3ra ASI package. It has definitions for entities such as materials, operations on them, physical properties, all the entities that we use across the platform. It's open on GitHub and available on PyPI. It defines schemas, and all the definitions are in the single consistent way. So when we say a slab, an interface, or a Miller index, it has one clear definition, and we can reuse it across the other stack. Second is example of the data stored in Mat3ra ASI, which has examples of the entities adhering to data standards from the ASI. Here we can see a list of materials that are named according to the categorization they belong to, so it's easier to find them, and they hold the structural information about each material. Third one is generic code base, Mat3ra code, which allows for the implementation of the entities inside Python or JavaScript. We're not going to be covering today, it's used internally. The fourth one is the specific code base, the main package for the design of 2D materials, Mat3ra Made. It has implementations for all of the main concepts like material, lattice, basis, has a set of functions to analyze and transform materials. All of the configurations, analyzers, and builders are stored here. It's available on GitHub and PPI as well. And the last one, fifth, is the example of the usage for Mat3ra made, stored in Mat3ra API examples. It has a collection of Jupyter notebooks. Those notebooks are constructed in a self-documenting manner so that you can use, so that you can open a notebook, see the transformation you want to create, see all of the implementation for the API, run the notebook, and learn how to use the tool. They can be used as day-to-day operations where you can create materials in your work. And they allow for easy collaboration because you can easily adjust them and share them. Final stage is making sure that this functionality is available to the end user. We support running notebooks in familiar Python, in a typical Python environment, such as Jupyter Lab and others, as well as to make sure it's easy to just open the web page where we have documentation, or if it's inside of web application, we allow for, we implement running these notebooks with the help of PyDiet, which is Python runtime in a web browser, so that you can open in a web browser and find the example that you want to run and just run it without the need to install or manage any infrastructure. You can use any pure Python package and, for example, PyMagen and AEC if you need those. Let's take a look at the implementation details. Ontology, what is the ontology that we implement? We split the creation of each material into three parts: the configuration, transformation, and the result. For example, if we want to create a slab, we would start with a bulk material, provide Miller indices, thickness, vacuum. This is our configuration. Then we take a builder, slab builder in this case, with the set of its own parameters that control how the structure is built. We apply the builder to the configuration, and as a result, we get material with the metadata describing the whole process. Metadata is stored for provenance. Sometimes the structure that we want to create is more complex, and you need a way to, you need more information that you know beforehand. For example, if you want to create an interface, you need to get two slabs. You can define two slabs, but then you need to make them coherent. So you need to provide a supercell for film and the substrate, and you need to provide the strain for the film. How do you do that? In that case, we split the process into three steps of define, refine, and then build. In the define step, you provide the definition for slabs for substrate and film. Then you take the interface analyzer with its parameters, like, for example, maximum area to search for the coherent interface. You apply this analyzer to the configuration, and as a result, you get multiple interface configurations that are ranked by size of the cell and the strain. For example, sometimes you need lower strain and you can tolerate a larger size, or vice versa. You select one that is more suitable for your use case, and then you take interface builder, you apply it to the interface configuration that you selected, and as a result, you get interface with the metadata storing the procedure that was performed on the starting materials. To make it easier to find specific transformation and reason about the materials, we came up with such categorization. First, they are divided into domains of pristine structures. For example, just a simple 3D crystal, compound pristine structures as interface, defective structures as substitution or vacancy, and process structures such as passivation. Further down, they divided by dimensionality from 3D to 0D. And as a result, you get final category. For example, a slab, an interface, adatom, interstitial atom, passivation. Some of the entries in the category have multiple variants. For example, how the structure was created. For the interface, you might have a simple interface where you don't strain match. You can have ZSL strain matching or commensurate lattice strain matching. And that's how different variants are formed. So this is the categorization. And today we'll be focusing on, it should say part 5. Today we'll be focusing on compound pristine structures of 2D interfaces mostly, of ZSL and twisted interface variants. Let's have a quick recap of the webinars that we had before. On the first one, we focused on introduction and creation of slabs and interfaces. So for example, here we can see the steps that we took to get the material from stand data, create a slab with using the function, and then get the material. Or we can define multiple slabs, or we can define 2 slabs, then we create them and then create an interface. And here's some examples of the structures that were created in that webinar. Slab with termination, with selected termination, simple slab, interface, and another form of interface. On the second webinar, we focused on nanostructures and heterostructures. So nanowires, where we set parameters for it, create a slab, and cut the nanowire. Nanoribbons, where we import the material, when we import 2D material and create a nanoribbon. And then the heterostructure, where we get multiple materials, create different slabs with different orientations, and then we use different stacking methods to achieve the heterostack. And as a result, we got 2 examples of nanowires with different orientation, 2 nanoribbons, zigzag and armchair, and the high K metal gate. On webinar part 3, we focused on point and surface defects, as well as grain boundaries. So you would import the material, set parameters for the defect or multiple defects, and create defect using the function. Get the result. You can get material, create a slab out of it, cut, select the box for the cutout, and create the island. Or you can get the bulk material for copper, select the terminations, select the orientation, and create grain boundary. So this is the example of materials that were created during the third webinar. Point defects, surface defects at atom and island, and grain boundaries on 2D and inside of 3D structure. Previous webinar 4 was focused on disorders, perturbation, and passivation, where we would take material created in the previous episode, nanoribbon, search for undercoordinated atoms, select those that we want to passivate, and apply passivation, get the passivated structure. We can do the same with the nanowire, where we recreate nanowire, and then we passivate it using the same function. And also we can create a supercell or a nanoribbon of any 2D structure and apply a function of some perturbation to get the perturbed structure. This is the examples of the materials that we had created during that webinar. So we have interface with some thermal disorder introduced, reconstructed silicon slab with passivation, passivated nanowire, and passivated nanoribbon. And what we're going to be doing today is that we're going to use Materials Designer application, open the Jupyter Light transformation inside of it, and open examples for specific publications. We're going to be creating structures from those publications. Simulations will be done in the next episodes, where we're going to be using the same notebooks to create the material, upload it to the platform, and then construct the simulation and reproduce it. It's going to be done later in the series. Today, we'll be focusing on 5 examples of different interfaces. So here we can see 2D on 2D interface, 2D on 3D structure, 3D and 3D interface. And then we're going to have another example of the interface using twisted commensurate superlattice analyzer and a simple optimization of interface. Let's start with this first paper, Graphene on hexagonal boronitride interface by Zhang Jail et al. Origin of the band gap in graphene on hexagonal boronitride. Here, the paper focused on the investigating the band gap that forms in the graphene when it's placed on the hexagonal boronitride. Usually, graphene has no band gap, but it develops one, and the size of it depends on the relative stacking to the surface to the underlying HBN, and the energy and the some of the positions are more favorable in terms of energy, and this is explored with the in plane translations. So if we go ahead and open the paper, then we can see this is what we've been reproducing. And what does it mean to reproduce a paper? We open a paper, we need to scroll down and find the material of interest that we want to recreate, for example here. Then we need to extract the information on how it was created. So what was the simple starting materials, what was the orientation, parameters of distances, any other properties that can define how the structure was created. So here we can get the stacking to understand how it was stacked. We get the sliding vectors that we can reuse in the notebook to encode the creation of this structure. So this is the result we want to achieve. 6, well, 7, but both are the same, finishing the cycle. So 6 final materials. We extracted the parameters. We can use graphene and hexagonal boronitride from Standata. Both of them have orientation of 0, 0, 1. We'll be doing the translation along y-axis with the vectors that we get from the paper, set the gap distance, and we should get multiple interfaces for the calculations downstream. The notebook for the reproduction will be structured as loading base materials, defining the parameters. Then we're going to build a slab with the create slab function that was covered in the previous webinars. We're going to build interface using create interface function. We're going to be shifting film using interface displays part, and we're going to save materials to the for the later use. And then we compare it to the configurations from the paper. So this is what we should achieve. This is the side view. Some of it can be a bit hard to understand just by looking at the side because of different settings for the repetition. So that's why you can see it from the top. Let's go ahead and open the Materials Designer. So materialsdesigner.mat3ra.com, standalone application to work with materials. We can go ahead to the View Jupyter Light session to open the Jupyter Light inside of this drawer. And here we would go to specific examples. And this was the interface 2D boronitride. We see the Python is running. We can run all cells so that it gets started. Again, we have a link to the paper, the example of the structure that we want to recreate. And here we set the parameters that we got from the paper. So for Miller indices for film and for substrate 001, thickness 1 for both of them. We don't need to give any film vacuum because the distance and the interface vacuum will cover that. We set the interface distance and some reasonable vacuum. I think it also was in the paper. Then we give the maximum area for the analyzer, for the interface analyzer. Here we got materials from Standata. We can preview them. Here it searches for the, further down we create slabs for the interface. So we search for terminations in case there's multiple. There's just one for each. We preview, this is just we preview the slabs of different terminations. And then we create slabs configurations for the substrate and film, providing the parameters that we define above. And then we feed those configurations into ZSL interface analyzer. It yields us multiple configurations. So this was our define step. Now we're on to the refine step, where we use analyzer. We get multiple configurations that are sorted by strain and area. And by default, it tries to get the smallest strain, smallest size. So this is the selected index. We can select any other type. And then when we select it, we can create, we can pass it to the same function to create slabs, and we can pass the selected interface to get that structure. And as a result, we get a structure that is created with simple, it's created in some position. We verify that it's some of the position that we might use, and then we do the shifts of the stacking position using the interface displays part function, and we pass the vectors with square root of 3 that we found in the paper, and we do it in the range to get multiple materials. Then we save them to the uploads folder, as well as we pass them to the materials designer, where if I make it easier to see bonds and add a bit of repetition, we can see the structure. And if I press shift down, I should be able to scroll. Yeah, so I can scroll to see material in a different position. So that's what we can preview them in different orientations. So this was the graphene on HBN structure. Next one is reproducing graphene on silicon oxide alpha quartz version interface. This is the paper by Kang, Electronic Structures of Graphene and Doping Effects of Silicon Oxide. Again, they investigated development of gaps in the graphene, and they found that substrate interaction can induce doping without adding any impurities inside of the graphene itself. So, and it depends, and doping effect depends on the surface polarity, if it's oxygen rich or oxygen lean environment. So that's why we need to create an interface. We need to create a slab either silicon terminated or oxygen terminated. Let's open the paper and again get to the structure we want to reproduce. This was the figure the first figure, we want to reproduce the structure, for example, for the silicon oxide that it was O terminated, and we place graphene on top of it. So we can extract information for all the properties. For example, bond length of silicon between carbon and oxygen is 1.45 angstroms. So this is our distance. The paper says that interaction between carbon and oxygen is strong, so that carbon moves to be on top of oxygen, and that's why we can use it as the distance for our interface. So we extract the information that we need. For example, graphene, silicon oxide, we can take them from some data, orientation 001 for both of them. We will select the termination of O2 for the silicon oxide, and we specify the thickness of 7 bilayers. So they treat, paper states that they used 7 bilayers, so they treat each conventional unit cell as a bilayer of silicon oxide. Again, we set the gap distance, and then we should get the materials. Notebook structure is going to be the same, where we load materials, define the properties, then we build 2D slabs, we create an interface, we select the most appropriate interface configuration, and then we save materials. And as a result, we should get this structure. And we need to note that the structure shown in the paper has relaxation, while ours for now does not. So that's why we can see that oxygens here are moved, oxygens that are positioned directly below carbon are moved toward the carbon, and that's why it introduces reconstruction of the underlying silicon oxide layers. That's why you see multiple bonds of different orientations, while here with the orthographic projection, we can see only one. So if you relax the structure, we should see that the oxygens move closer to the carbon, and we should see some reconstruction there. So maybe let's close this one. Again, opening Jupyter Lite session. Specific examples, and this is 2D on 3D example. We can run the notebook. So this is the structure we want to reproduce. We specify Miller indices for graphene, for the interface, for the silicon oxide, substrate thickness, and we pass the termination formula, and we set interface distance that we got from the paper and the interface vacuum. Then the settings for the analyzer. We should get the materials from StanData and preview them here. Then we get down to the getting of the terminations for both of the slabs. So graphene will have just one termination, while for silicon oxide, we're interested in the multiple terminations, and we want to subselect the O2 termination. So here we preview all of them, and these are the two that are needed for us. One either will do. And this is the silicon terminated one. We can actually create the other example as well. We select the termination that we provided at the settings level, and then we on to creating the slabs configurations. Again, we just configure the slabs, get to the refine section where we use Z-cell interface analyzer, pass the configurations for both of the slabs, and we scroll down to see the trade-off plot. Select the index 0. We create the slab using create Z-cell interface function. We pass to slabs all the properties, and as a result, we should get the structure. that was mentioned in the paper. And here we set materials to the materials designer, as well as we download content to the file. So that's why you saw the materials being added to the downloads folder when the notebook ran. You can review the structure here as well. Bonds. So this is the structure that we want to that we recreated. So I used the orthographic camera projection to remove the distortions and to see how exactly underlying layer is positioned against the graphene. Again, you can use displace interface part to move it around and then use the structure later to relax it and get the structure that is closer to the one in the paper. So next one is the reproduction of structure from copper. So the paper was focusing on reviewing interaction between copper and silicon oxide, molecular dynamics study of the adhesion of the copper silicon interfaces. Metal oxide interfaces are critical in the microelectronics, so it's important to understand how adhesion works. And they found out that the adhesion depends on the oxygen content of the top layer. So if it's oxygen terminated, so oxygen rich, or if it's oxygen lean and silicon terminated. And they want to create a structure and calculate the adhesion energy. So if we go to the paper, we want to find the structure, and it was provided in an appendix down below here. So the first example is the structure that we want to recreate. So the copper 001 on oxygen rich, oxygen 2 terminated silicon oxide. So this is the structure. We get information about the properties for the distance and for the orientation from within the paper. Then when we extract it, we can set the orientation to materials, orientation, and gap distance that we found from the paper. Then we use the same notebook structure as before to load materials, define the properties, build slabs, create an interface, and save the material. And as a result, we should get a structure that is similar to one that we have there. So again, important to note that the structures they have has some relaxation, as you can see, because oxygen copper interaction introduced strong coupling, and that was what restructured the top layers of the silicon oxide. So here we do not do any relaxation as of now. And also the cut is a bit different, so that's why oxygens that the cut that we're viewing from is a bit different. So that's why oxygens that are present here are not shown here. They should be in the next unit cell. So that's why we have a bit of differences. If we go ahead and open Materials Designer again, open the same drawer, specific examples. This was the interface between 3D and 3D structures. Here we see the example of the paper, example of the images that we want to recreate. Then we set the parameters for the silicon oxide and graphene. We provide the values from the paper, distance, the vacuum that we had there, and then we provide the settings for the analyzer. Then we wait for the installation of the packages. We should, again, get the materials from the data, where we search for copper and cristobalite colloquial names, and we should get materials to preview. After that, we're doing the same thing as in the previous example, where we search for different terminations. Again, oxygen-rich and oxygen-lean terminations. We preview them. This is the one that we need. We select it because we passed termination at the top, or by default it's going to be the zeros one, so it's what we need, the oxygen one. We have the slab configurations again for the substrate film, passing the same parameters that are defining the slab, and then we use the cell interface analyzer with a set of parameters to get to the plot. And I think this looks like the smallest strain. Okay, so here we have the smallest strain on the index 0, but this is kind of large structure, so that's why here I opted to get to the index 1, which a bit more strain, but it gets us to the smallest area, which is closer to what they had in the paper. So that's why we have, if we select first one, we get this structure. We can also try to select to the zeros interface and previsualize it a larger structure. Let's see the result. Bonds. Probably we can use orthographic camera as well. Maybe to make it easier to compare with the paper, I should, yeah, let's see, okay. Excuse me. Yeah, I wanted to make the structures a bit larger. So from the side, we can see that this is the structure that we got. If we close this one. Okay, maybe bonds were changing the speed of the loading. So if we look at the side, we're going to see the same structure that were in the paper. Okay. So we should get the structure like this. Next one is reproducing twisted interfaces of twisted bilayers of molybdenum disulfide, which was done by team of Ting Cao and Kaihu Louis. Sorry if I pronounced it incorrectly. Evolution of interlayer coupling in twisted molybdenum disulfide bilayers, where they reviewed creation of the band gap in twisted molybdenum disulfide layers. They found this depending on the stacking, and that the stacking distance is also dependent on the that the distance between bilayers is dependent on the relative orientation. So molybdenum with molybdenum they repel, while molybdenum and sulfur interaction attracts. So if you have a position where you have two molybdenum atoms on top of each other, we have larger separation, while where the molybdenum is closer to the sulfur, we have closer distance. While for the different orientations, when you do rotations, the interactions cancel each other out and they have all the same distances. Again, this was the information is from this paper. If we scroll down, we can see that the structures that they were focusing on creating, and then they ran the calculations to get direct and indirect band gaps for the subselection of 6 of them. So we're going to be focusing on creating the subselection of 6 of the materials. So we extract the information, molybdenum disulfide, we have it in the stand data, then we set the orientation for both layers, we get the rotation angles that we use there, and shifts for the stacking will be done with passing just 0 and 60 degrees angles to rotate them relatively. And we also get the gap distances depending on the stacking orientation. The same notebook structure where we load materials, define slabs, create twisted interface to create this interfaces, because this is the one that this is the analyzer that does not introduce strain, but we can control the relative angle of the two commensurate lattices. Then we're going to be saving materials for the later use. So if we go ahead to the the previous structure actually. So this is the structure from the previous one. So we can look at it and compare with the results. So if we go ahead and open JupyterLite session, let me just restart this. If we open JupyterLite session and we go to the specific examples, in this example, we see the explanation of the structure of the notebook, how it's going to be run, the example of the paper, the structure from the paper, and here we set multiple interface parameters that are going to be used later. It's just the thing is that for angles of 13 and 47 degrees, the search takes 1.5 minutes. So to make it faster today, we're going to skip those. You can uncomment them if you want to get all of the structures. So we can go ahead and run all cells to install packages and run the notebook. So we specify for interface parameters angle and the distance that we got from the paper, specify Miller indices, number of layers for both of the slabs, and some reasonable vacuum. This is the search algorithm this is parameters for the search algorithm for the commensurate supercell analyzer. You can specify maximum repetitions of the supercell matrix, and you can pass none if you don't know it yet, and the algorithm will find some automatically. We need to pass angle tolerance in degrees to make it easier to search for structures that are close to the target ones. So we install the packages, got the material from stand data by searching molybdenum disulfide and 2D version of it, because we also have the 3D version that has no vacuum in Z direction. We can preview it. Then we create a slab for simple slab. And then here we build multiple interfaces. So create commensurate interface is the function that we use, where we pass the slab, the target angle, angle tolerance, maximum repetition, and other properties for the analyzer. And so the direction of the stacking gap between the structures, again, depending on each of the, for each of the configurations is different one, and the common interface vacuum. Here we don't have the plot because we just search for exact match for the angle. So we do not control the size of the structure, because for some angles of 0 degrees or 22 degrees, it's a simple structures. For example, for the 20s, for the 13 degrees, the structure is going to be have 114 atoms, so it's going to be 4 times the size, and it all depends on the time to get material, and the final result depends on the orientations. And we can save them, download to the file system, and we can preview the structures here. Maybe we can lower this for molybdenum sulfide, and so this is structures of different orientations. The paper provides only views of the single hexagons, and they collapse the two molybdenum they collapse two sulfur atoms into one sphere. So that's why it's a bit different from what we have here. But the angles are correct, and this is, if we look at one of the, let's find some useful. If you look at one of the hexagons, we can see that this is how it's located. So molybdenum is over silicon, over the sulfur, and this is the relative rotation. Next one is the example of simple optimization of interface of graphene and nickel 111, paper by Arjun Dahal, where they had an overview of graphene nickel interfaces. Interaction between graphene and metal interface is driven primarily by the mismatch of the lattice and the interaction strength between the metal and the carbon. And the interaction controls the separation of graphene metal layers, as well as structure for the as well as the electronic structure of the graphene. So some of the materials are weakly interacting and some interacting strongly. So for different materials, we would have different most optimal positions of the graphene layer. This is the paper that we're going to be reproducing. They describe how what's the distance between each of the orientation of the metal and the graphene metal separation. So we can find for the nickel it's 0.1 nanometers, and the electronic structure is changed drastically compared to other materials. If we scroll down to get the structure for the schematic structure for the graphene nickel interface, we would see the most optimal energy configuration, and we also see that some buckling of graphene is occurring. So this is the structure we want to reproduce. The only difference is that So this is the information that we got from the paper. Orientation for materials, gap distance, depending on the orientation. And okay. So the notebook structure is going to be similar, where we load materials, define them, we create a slab, we create an interface, and then we're going to be creating interface displacement to shift film relative to the substrate. And we're also going to get most optimal displacement by passing interface and passing a calculator. The calculator is a simple sum of inverse squares of the distances, but it gets the job done in this particular situation. So here we're going to reconstruct this structure, and we need to note that while here the buckling and some reconstruction of the nickel surface is present, we're not going to get this today, because where we're doing the relaxation, where we're doing the optimization, we just move the film in XY direction as a rigid object. So we don't have any reconstruction here. So we need to run some relaxation or other optimization strategies to get to the exact reproduction. So if we open Jupyter session, again, specific examples, optimization interface of film for XY position, the same structure of the notebook as before. Let's run all cells. Here we specify name for substrate and film so that we can get them from stand data later. We pass settings for the film. So graphene 001, thickness of 1, no termination. We pass settings for the substrate, nickel 111. We're going to be using thickness of 4 atoms, and interface distance can be set to be one matching the largest distance with the unfavorable position, or 2.1 angstroms for the most favorable position. And then we provide parameters for the interface analyzer. And further down, we specify what is the size of the grid for XY optimization, so the range of it, and whether it's a Cartesian or not coordinates. We also can set the 3D landscape to true to have a nice preview of 3D landscape, of the energy landscape in 3D. Maybe let's rerun it. So here we specify, again, define stage, we define the slab configuration. We then create an interface by passing the 0th index, choosing the 0th index, because we know it's going to be the smallest strain and smallest size selected. Then we get a structure with some position, some default relative position, and as we can see here, it's in this position. So this is what we have by default, hollow side, and the most favorable position is the top side HCP. So we need to get here. Right now we have this one, and we need to get to the other one, or whatever is most optimal by judging by the energy. So we add the calculator, interface material calculator, which is simple calculator that uses inverse squares of the distances as the energy, as the effective energy. And then we evaluate this calculator on XY grid, and as a result, and we get the most optimal interface by using the function get optimal film displacement, passing the interface, passing the calculator, and the same parameters. This is used to map. This is used to map the landscape. So here we can plot it. Okay, so this is the 2D plot, and then this is the 3D plot where we can see two symmetrical positions of the optimal positions. I think both of them might be suitable. It selects the most optimal one in this case. And as we can see, we moved from hollow side to HCP atop. So this is the third layer, third atom, and graphenes are placed on the topmost atom. So I think, yes, so this is the first structure that was created with no optimization. If we make it larger. Okay, no, we in both cases, okay, in both cases we pass just the one, we pass only the optimized structure, I think. Yes, we save only the optimized structure. So yes, this is the final structure that we get. And this is the correct position. So now let's see how those notebooks can be accessed. Notebooks can be accessed from jupyterlight.mat3ra.com. If we go there, we can see the notebook that opens, and examples for the made are in the made folder. Here we can scroll down. If we open the introduction notebook, it has the all of the notebooks available to us in the listed in the categorized manner, and we can open, for example, interface creation, or we can go to the specific examples where we can open the notebooks for the reproduction of specific papers and run them here. Also, notebooks can be accessed by Materials Designer web app, as we've seen before. And inside of the tutorials in the documentation. So if we go to docs.mat3ra.com, on the top level, we can see tutorials and reproducing specific manuscripts. And if we go to the overview, we can see the overview of all of the available examples. So again, this is what we looked at today. We can open the example and follow the tutorial to see how you can reproduce the structure using different notebooks. And at the bottom here, we should see the notebook. Okay, this is strange, but for all of them, yeah, you should see the notebook that shows that you can run, and you can run all of the creation of the materials. Also, this materials designer is available on the platform. So if you go to the platform and open the materials section, we should see the if we go to the materials designer, we should see the ability to open the JupyterLight session in the same way. So now we can get the materials and create a supercell and run all of the functionality inside of the platform and save materials to your collection and use them for the calculations. So in the next episode, we'll be covering reproduction of the papers, where we focus on point defects and surface defects. So it's going to be some of the structures that we're going to cover in the next episode in February 25. So today we've looked at the Mat3ra made package, a Python framework to create 2D materials design, 2D materials. We showed how to use them using Mat3ra API examples package, which provides examples of different 2D materials and interfaces. We've shown that we can access them via JupyterLite Mat3ra.com, on Materials Designer, or from the documentation, where we can see, where you can access the interactive tutorials and run examples. All code is open source and available on GitHub, and we welcome contributions. So now on to the questions.
All right, thank you, Seth. We are over time, unfortunately, with the presentation, so there might be time for one quick question if we do have it. I don't think there is anything in the chat just yet, so I think this will suffice. We understand how to access the specific examples, how to access the notebooks. We'll continue next month. Thanks, everybody. Thank you, Seth. See you next month.